This video is sponsored by PCBWay. More about them later. I found this hoverboard for around $20. Hoverboards are everywhere, and since no one really uses them anymore, you can get them really cheap. And inside you get 2 brushless motors and a battery pack with built-in BMS. Problem is they're really slow, but my research suggests that the motors are capable of going pretty fast. The stock controller is programmed with a speed limit to keep the rider safe. Once a certain speed is reached, it reduces or stops increasing power to prevent further acceleration. By using a custom controller, the motor can operate at higher speeds, provided the battery can supply the required voltage and current. Wheel size also affects top speed. Increasing the wheel diameter means the motor covers more distance per revolution, which results in higher speeds. So instead of using the original electronics, I decided to design my own controller. To actually design a controller, we first need to know how a BLDC motor works. A brushless DC motor works by coils that create a magnetic field and attracts a magnet. By alternating what coil we power, we get a spinning magnet. The brushless motor we are using works a little differently. Instead of having the magnet inside of the core, we have the coils in the core and then magnets around the coils. But it works the exact same way. Here you can see the signals that it generates when I spin it manually. To actually spin a motor not by hand, we need to recreate 3 of these signals. This website has a great demonstration of how it works. But instead of using switches or buttons, we are using MOSFETs. But there's one problem. How does the controller know what coil to power? There are 2 main ways to know this. There's something called FOC and something called Hall effect sensors. Our motor has Hall effect sensors. It works by sensing a magnetic field and then knowing the position of the motor. It actually has 3 different Hall effect sensors, which it uses to decide which MOSFET to turn on and off. Now that we know how it works, we know exactly what to make in order to control the motor. First I stole some MOSFETs from the original board. Their legs were too short to put into a breadboard, so I soldered these legs on them. A MOSFET gate acts like a small capacitor and typically requires around 10 to 12 volts between the gate and the source to fully turn on. Since most microcontrollers only output 3.3 volts or 5 volts, they cannot drive the MOSFETs efficiently by themselves. A gate driver solves this problem by providing the higher voltage needed to switch the MOSFETs. I decided to use an IR2130 gate driver. This driver can control all 6 MOSFETs. Many other gate drivers only control 1 high side MOSFET and 1 low side MOSFET. These are what high side and low side MOSFETs are, by the way. That meant I had to control all 6 MOSFETs manually and handle the communication in code. And honestly, I never really got it working properly. I even managed to destroy a couple microcontrollers, and then I used some optocouplers to fix that. I mean, come on, just watch this video. Look at how close I came. Look, I paused the signal and it's not right. It's that the phases are at the same time, which is not correct. They're supposed to be after each other. And the motor is making this weird noise. And I even found this guy on YouTube and he made it work and I got jealous. So obviously I changed approach. Instead of doing everything manually, I used a smarter driver. The A4915. This chip reads the Hall sensors from the motor and just handles the communication internally. This means instead of generating all the switching signals myself, I only need speed input, direction and enable, which makes the system much more simpler. There was one problem with the A4915 though. Unlike the IR2130, it's only available in a tiny SMD package. That meant I couldn't just throw it onto a breadboard and test it first. If I wanted to know whether my design worked, I had to commit to a PCB and hope I didn't make any mistakes. So this was basically a gamble. Luckily, PCBs from PCBWay are surprisingly affordable, so ordering a board wasn't a huge risk. The expensive part is actually the components. If the design doesn't work, it's not the PCB you're worried about, it's the parts that's soldered onto it. So I double-checked almost everything and crossed my fingers and sent the design off for manufacturing. PCBWay handled both the manufacturing and assembly of this board. which was really useful because working with small SMD components is exhausting. And instead of soldering it myself and probably ruining it, a professional gets to solder it. Ordering was actually pretty straightforward. I just uploaded the manufacturing files, then selected things like the PCB color, thickness, and a few other manufacturing options. A few days later, they sent me photos of the assembled boards before shipping, which was nice because then I could verify that everything looked correct before they were sent out. The board quality came out really clean. The soldering was sharp and everything looked great. The silk screen matched the design exactly. Another thing I really appreciated was the customer support. Whenever I had a question, they responded quickly, were professional, and kept me updated throughout the process. The communication was clear and transparent from start to finish. And most importantly, this is the exact board that's controlling the motors right now. That being said, I still managed to fry a few of these chips, so I had to replace them myself, which meant doing SMD soldering. And I had to replace the chip multiple times. A big issue turned out to be the power supply. The buck converter for the logic voltage wasn't working properly, which caused the whole system to fail. And this was obviously entirely my fault and a design error on my part. Instead of taking the 36 volts that comes in and turning it into 5 volts for the logic, it just lets 36 volts pass right through. By scratching the trace that leads the 36 volts to the buck converter, I fixed the problem temporarily and get it to work with a lab power supply. The reason it stops spinning is because I let go of the gas pedal and I don't want the wires to get tangled. I made this little board to control all of the inputs that goes to the board. This is what I mean by inputs, and they need to go to both of the PCBs that control each motor. For the actual cart, my initial idea was to take this kid's toy and put some motors on it, but it didn't fit me at all. It was way too small, obviously. So I decided to cut it in half and turn it from this baby car to this cool gangster looking car by making it longer. Me and my cousin welded some extensions on it, so it got longer, but it was really wobbly and not stable at all. So I decided to just make my own cart. It got pretty good and I stole the front wheels from the kid's toy. And I also got this chair from the local junkyard and just welded it onto the frame, as you can see here. I also made the steering system. It's not the best, but it works decently. And I made these holes to fit the actual motor. This is the steering system on the front, so I 3D printed some plastic things with bearings in them to turn better. Fixing the power for the logic wasn't that hard. I just used an LDO with another battery with less power. I mounted all of the electronics to the frame, but it didn't work properly for some reason. It wouldn't even spin one wheel. So I took it back on a bench and started troubleshooting. I got it running, but only on 12 volts, which was weird because 36 volts worked just fine previously. And also the controller is designed for 50 volts. Because of this, I had to replace the IC a couple of times, because when I tried running it with 36 volts, it just died. At the end, I just decided to use 12 volts to see what it could do, but that means it's like way slower and weaker than it's supposed to be. This is a clip of me connecting it to 36 volts, then trying it. And it dies instantly. This video is already starting to get pretty long, and honestly, I have not come much further with this version yet. So I'm going to call this version 1 and then make a second version of the go-kart with the upgrades it clearly needs. This means a redesigned controller, a proper power supply, stronger MOSFETs, better cooling, cleaner wiring, and hopefully enough voltage to make it actually fast. Thanks again to PCBWay for supporting the project and helping me bring this design to life. And if you want to see the next version, you should probably subscribe so you don't miss out on a new video.